Here I am discussing second numerical problem on Laplace equation. This problem is in Cartesian coordinate system because the vector D is having y component. Let us see what is given in the problem. Solution. The problem says that there are two parallel conducting planes. Two planes, both are parallel. Conducting planes, both are parallel conducting planes in free space, and they are located at y equal to 0. So the first plane is located at 0. The second one at y equal to 0.02 meters. And the zero reference means v equal to 0 is located at y equal to 0.01 meters. In our regular problems, one of the planes is grounded. One of the planes is taken at the potential 0. But in this problem, they have given the zero reference potential at y equal to 0.01 meters. That means first plate is at y equal to 0, second at y equal to 0.02. So 0.01 is the plane in between these two conducting planes. This is y equal to 0.01 meters at which potential is 0. Next, the vector D is given 253 nanocoulomb per meter square. It is the y component. This D is distributed between the two conducting planes as usual. Now we have to determine the conductor voltages. Usually in regular problems, conductor voltages were used to be given. But in this problem, we have to find the conductor voltages. That means we have to find the voltage on the first conductor. Let it be V1, second conductor V2. So we have to find here the values of V1 and V2. So for that we need boundary conditions to solve the Laplace equation. But here one plane is given and at which potential is also defined. V equal to 0 at y equal to 0.01. We can take this as a boundary condition. Second one, instead of another condition, they have given the vector D. So I have to make use of D to find an arbitrary constant after solving the Laplace equation. So let us start solving the problem using Laplace equation. First point, why Laplace equation? Because between the two conducting planes, there is a insulating space region in which no charge is distributed. So this is a region of Laplace. Second one is the problem is speaking about potential values at the different planes. So Laplace equation is the right one to address a system for which potential distribution is given. So let us start with Laplace equation. Del square V equal to 0. The problem is in rectangular coordinate system, RCS. Therefore, the expansion of Laplace equation is given by this equation. That's it. We have the expansion of the Laplace equation. From the problem, we can say that potential V is a function of Y only. V is a function of Y only. There is no specification of X and Z. Therefore, from the previous equation, only middle term is enough. D square V by dy square is enough. The first term and second term, that is dou square V by dou X square, dou square V by dou Z square, are 0. So we have only one term in which potential V is present. We have to integrate this equation twice to bring this V outside. Let me integrate it first. The first integration gives us dv by dy. Integration of 0 is 0 plus constant of proportionality C1. C1 is any arbitrary constant. Now one more integration on the left hand side gives us V. On the right hand side, integration with respect to y gives C1y plus C2. In one of the videos, I had discussed the potential distribution of a parallel plate capacitor. There also we got a similar equation, and there we discussed that potential varies linearly between the two conducting planes. Here also, same type of equation is obtained. V is equal to C1y plus C2. C1 and C2 are arbitrary constants. So let us find C1 and C2. For the two boundary conditions are needed, but only one boundary condition is given. In another one, an expression for flux density is given instead of the boundary condition. So therefore, let us use the given information here to find C1 and C2. So the given is V equal to 0 at y equal to 0.01 meters. So this information is given. Therefore, equation 1 now becomes equation 1 now becomes 0 equal to C1 in place of y 0.01 plus C2. So therefore, C2 is equal to minus 0.01 C1. Even though C2 is not completely calculated, some relation is obtained related to C2. Now we have to use another condition, that is D equal to 253. That is also given that D equal to 253 A cap Y nanocoulomb per meter square. So if you find an equation for D, we can substitute this numerical value 253 into that one. Therefore, we shall start from equation 1 and we'll find D from this V. You know that from V we can find E, then from E you can also find D. Therefore, from equation 1, okay, so you know that equation 1, and let us call this equation 2. From equation 1, we can find E, that is E is equal to minus del V, negative gradient of potential. So expansion of del V in Cartesian coordinate system, and V is the function of y only. That's why I directly write this as dV by dy a cap y. That is our E, because dou v by dou x and dou v by dou y, dou v by dou y, dou v by dou z, all the three components will be present in E. Among them, dou v by dou x and dou v by dou z is 0. Now, we have to differentiate V, and in equation 1, V is calculated as C1y plus C2. This is to be differentiated to get E. So E now becomes, after differentiation, C1. Differentiation of y is 1. Differentiation of C2 is constant. Being constant, it's 0. So we got an equation for electric field intensity in terms of volts per meter. But we want D. Therefore, D equal to epsilon naught E. The problem, it is mentioned free space, so epsilon naught. So we are going to have now minus epsilon naught C1 a cap y, the D value, coulomb per meter square. But in the numerical, D is given. I would like to use that value now. That is, D is given as 253 nanocoulomb per meter square a cap y. It's a y component. Epsilon naught C1 into a cap y. So from this equation, C1 becomes 253 nano minus epsilon naught in the denominator. This can be further calculated using the value of epsilon naught, that is 8.854 into 10 power minus 12. So from this, we can find the value of C1 as minus 28.6 into 10 raised to 3. So one constant is found from the value of D. Now we have to find the second constant of integration, that is C2 from equation number 2. See, here is equation number 2. C2 is equal to minus 0.01 C1. So we shall complete the calculation of C2 now. Therefore, C2 is equal to minus 0.01 C1, that is equal to minus 0.01 C1, that is minus 28.6 kilo, becomes becomes plus 286.14. C2 is a positive value because of minus into minus plus. So C1, C2 are calculated from the given value. Therefore, V in equation 1 becomes, so what is there in equation 1? V is equal to C1y plus C2. So V is equal to C1y plus C2. This is equation 1. So C1 is 28.6 into 10 power 3. This is C1 into y plus C2. C2 is 286.14. So finally, we have found the potential distribution between the two conducting planes defined by this equation, that is in terms of volts. But the question is to find conductor voltages. What is the voltage at the first conducting plane, then voltage at the second conducting plane? That means we know that there are two conducting planes, one located at y equal to 0, another one at 0.02. And I have taken this voltage of the first plane as V1 and the second one V2. We have to find V1 and V2, right? So using this location data of V1 and V2, we can find V1 and V2 from this equation, let us say 3. V is equal to V1 at y equal to 0. Therefore, from equation 3, so equation 3 gives potential field voltage at every point. From equation 3, V is equal to V1. I'm going to substitute this V as V1 minus 28.6 10 raised to 3. In place of Y 0, 286.14. Finally, V1 is equal to 286.14 volts. This is the conductor voltage at the first plane. Similarly, I would like to find the voltage at the second plane. V is equal to V2 at y is equal to 0.02 meters. Second conductor voltage. Again from the same thing, from equation 3, we get, in place of V, we write V2 minus 28.6 into 10 power 3. In place of Y, we have to write 0.02 plus 286.14. So in the equation 3, in place of Y, we have written 0.02. So after solving this, we get V2 as minus 286.14 volts negative. That is. So these are the voltages, that is V1 and V2 are voltages of conducting planes. Voltage of conducting planes. This makes the solution of this problem. Thank you.